In December 2021, humanity unfolded a mirror a million miles from home. The James Webb Space Telescope, gold-paneled, delicate and vast, became our newest eye on the cosmos. It was designed not just to see farther, but earlier, capturing light that began its journey billions of years ago. Webb's strength is subtlety. It does not look for brilliance, but for signatures, faint absorptions in starlight, tiny wobbles in orbits, whispers in infrared. From these whispers, it can tell the difference between hydrogen and water vapor, between barren rock and chemical complexity. When it first began scanning exoplanets, worlds orbiting other stars, few expected revolution. Most imagined incremental progress, better data, refined measurements, another brick in the patient wall of science. And then came the spectrum. The data arrived quietly, one of thousands of light curves sent to analysts on Earth. Webb had observed a planet orbiting a red dwarf star about 120 light-years away in the constellation Leo. The planet, known to astronomers as K2-18b, was already intriguing. A sub-Neptune in the star's temperate zone, large enough to hold an atmosphere but small enough to be rocky beneath its clouds. Webb's spectrometer, tuned to the infrared, dissected the starlight that passed through that atmosphere as the planet transited its star. The resulting pattern, peaks and dips across wavelengths, told a story written in molecules. At first glance, there was water vapor, then methane, then carbon dioxide. But most striking of all was a narrow, persistent feature that matched models for dimethyl sulfide, DMS, a compound produced on Earth almost exclusively by living organisms. The signal was faint but real, recurring across multiple transits. Statistically, the chemistry of K2-18b's atmosphere now aligned with what scientists call a biosignature stack, a combination of gases that, in equilibrium, should not exist without continual biological replenishment. Some estimates put the likelihood of an abiotic explanation below 1%. The phrase that circulated through labs and newsrooms was cautious yet electric. A 99% chance of life. K2-18b is not a second Earth. It is larger, about 2.6 times Earth's radius, and its gravity nearly 10 times stronger. Its star is smaller and cooler than the Sun, bathing the planet in dim copper light. Yet models suggest an atmosphere thick with hydrogen and water vapor, perhaps blanketing an ocean thousands of kilometers deep. If those models are right, the world could be what astrophysicists call a Hycean planet, a hybrid between hydrogen and ocean with conditions suitable for microbial life. Beneath perpetual twilight, warm seas may churn under clouds rich in methane and vapor, their chemistry alive with possibility. To imagine such a place is to stretch one's mind beyond terrestrial comfort. There are no continents, no skies as we know them, only a vast ocean world orbiting a red sun, its surface pressure immense, its winds slow but constant. Yet somewhere in those alien depths, molecules might assemble, divide and adapt, just as they once did in the ancient seas of Earth. For scientists, this discovery is not confirmation but conversation, a signal strong enough to compel new models, more observations and deeper humility. For the rest of us, it is a turning point, the first plausible glimpse of another living world. Science moves slowly, deliberately. One observation does not make a discovery, it begins a debate. Within days of Webb's data release, research teams across the world began reanalyzing the signal from K2-18b. Skeptics asked the right questions. Could the DMS line be noise? A calibration artifact? Could volcanic chemistry, photochemical reactions, or even unseen instrument drift mimic life's signature? Others ran atmospheric models with alternative gas ratios. None could easily reproduce the pattern without invoking biology. Peer reviewers reminded the community, extraordinary claims require extraordinary evidence. Yet privately, even seasoned astronomers confessed something they rarely say aloud. This one feels different. For decades, biosignature searches ended in frustration. Mars had ambiguous organics. Venus teased phosphine that later dissolved in reanalysis. But K2-18b's case was statistically strong, reproducible, and, most importantly, chemically consistent with metabolism. The debate shifted from if to how certain. In closed sessions and late-night conferences, scientists argued over priors and probabilities, but few could deny the thrill. Perhaps for the first time, humanity had seen not just a planet, but a living system beyond the sun. But what does life mean on a world like K2-18b? The word conjures forests, coral, birds, and breath, yet life in the cosmos is likely stranger, quieter, more subtle. On this distant planet, evolution might play to different rules. Under a hydrogen-rich atmosphere, cells, if they exist, would need chemistry adapted to pressure and scarcity of oxygen. Photosynthesis, as we know it, would be impossible beneath the copper light of a red dwarf. Energy might come instead from chemosynthesis, organisms feeding on methane, ammonia, or trace radicals. Imagine microscopic organisms drifting in warm, dense clouds, feeding on light filtered through vapor, or living deeper, in oceans beneath the mist, converting dissolved gases into simple sugars. Even here on Earth, extremophiles thrive in boiling vents, acid pools, and Antarctic ice. Life, once it begins, finds a way to persist. K2-18b could be another expression of that stubborn universal impulse, the tendency of matter to organize, to reproduce, to endure. For astrobiologists, this discovery reshapes the search. If life can arise on a Hycean world, then it is not confined to Earth-like planets. It could exist wherever chemistry can dance, across the galaxy, in forms as diverse as imagination allows. Every generation of astronomers has its frontier. Galileo saw moons around Jupiter and proved that Earth was not the center. Hubble saw galaxies and proved the universe was vast. The James Webb Space Telescope, in its quiet way, may have done something equally profound. It may have shown that we are not alone. The data teams have become modern cartographers of existence. They do not draw coastlines but spectra, faint signatures of water, methane, carbon dioxide, and dimethyl sulfide. Each peak and trough in the graph is a new kind of geography, an atmosphere charted by light alone. Already, the Webb Consortium has planned follow-up observations. Multiple instruments will re-examine K2-18b, testing for seasonal variations, verifying that the DMS feature persists. If confirmed, the next step will be ambitious, sending future telescopes, the Habitable Worlds Observatory, perhaps even interstellar probes within centuries, to map the planet directly. The first map of Earth was drawn from ships. The first map of an alien biosphere may come from photons that traveled for 120 years before touching a gold mirror 1,000,000 miles away. The news did not arrive as thunder. It began as a whisper. An embargo lifted, a headline shared, a cautious announcement during a quiet afternoon press briefing at NASA's Goddard Space Flight Center. The James Webb Space Telescope has detected a combination of atmospheric gases consistent with biological activity on the exoplanet K2-18b. Within hours, the story had circled the globe. Every newsroom, every podcast, every social feed lit up with a single, unanswerable question: are we not alone anymore? Reactions were immediate and human. Some celebrated, some doubted, some prayed. Religious leaders reflected on creation. Philosophers invoked Copernicus. Politicians promised funding for further study. In classrooms, children asked the simplest, most profound question of all: what are they like? For most scientists, the answer remained disciplined: we don't know yet. But beneath that restraint pulsed something electric, a shared awareness that the wall separating humanity from the rest of the cosmos had thinned. The Webb telescope had not found intelligent life, nor cities, nor signals, only gases, ratios, probabilities. Yet the implication was enormous. The first sign of life beyond Earth was not a broadcast or a landing, but a spectral fingerprint, light interpreted by mind. Why 99%? Because in science, certainty is sacred. 99% does not mean absolute truth. It means confidence so high that error is improbable, yet not impossible. This restraint is not weakness, it is strength. It is how science protects wonder from wishful thinking. The data show an atmosphere that, if abiotic, would require chemistry unlike anything modeled in planetary science. The ratios of methane to carbon dioxide, the persistence of water vapor, the faint but repeating DMS signature, all align with what life as we know it produces. But as we know it is the key phrase. There may be chemistries we do not yet understand, reactions not yet catalogued, possibilities that mimic biology but are purely physical. So the scientists keep observing, keep doubting, keep refining, because the true miracle is not in the claim of life, it is in the method that tests it. Still, for the rest of us, that number, 99%, lands with the weight of revelation. It means that the cosmos, long imagined silent, might actually be murmuring back. For months after the announcement, humanity lived in a state of quiet awe. Art, music, and literature reflected a new cosmic intimacy. Late-night television hosts cracked jokes about space fish. Streaming services commissioned documentaries. But beneath the noise, something subtler changed. A shift in self-perception. For centuries, we looked up and saw stars as distant, eternal, indifferent. Now, one of those points of light carried the whisper of life. The night sky became personal again. Religions reinterpreted ancient texts in cosmic context. Environmental movements invoked the discovery to remind humanity that life, any life, is rare, fragile, and precious. Governments convened to discuss new planetary protection policies. Even economics responded. Investment in astrobiology, spectroscopy, and off-world research surged. Humanity had been given what no revolution or war could deliver, a common horizon. For the first time since the Apollo landings, people everywhere were united by curiosity instead of conflict, wonder instead of fear. For millennia, humans have drawn maps that end at the edge of the known. Beyond those borders, they wrote, "Here be dragons." Now our maps stretch across the stars, but the instinct remains the same. We fear and wonder about what lies beyond. The discovery on K218b doesn't erase that boundary. It redraws it. Life, once the most parochial thing imaginable, confined to our oceans and soils, now becomes a cosmic phenomenon. We begin to see Earth not as an exception, but as an example, one expression of a larger law of nature. Wherever conditions permit complexity, the universe seems to experiment with it. The implication is vast. If microbial life thrives in the clouds of K218b, it may thrive elsewhere too, in the methane lakes of Titan, in the subsurface oceans of Europa, in the atmospheres of other Hycean worlds orbiting faint red suns. The human story, long written in isolation, suddenly acquires a plural form. We are not the living world. We are one among many. And in that realization, humility and purpose meet. What happens to a civilization when it sees itself reflected across the void? For centuries we looked outward and found emptiness. Now in the dim light of a distant star, we see a mirror, not of form, but of function. Somewhere, perhaps beneath alien clouds, chemistry has learned to feed itself, to persist, to evolve. Life out there does not make ours less special, it amplifies it. It shows that the laws that shaped us are generous, that nature writes its signature in many hands. And so the Webb telescope becomes not only an instrument of observation, but of reflection. It shows us that the universe is not silent, it is creative. Every atom, every photon, every molecule participates in the same grand experiment, the tendency of matter to organize into meaning. The mirror also raises questions about destiny. If life is common, will intelligence follow? Will technology arise again and again, scattered through the spiral arms like seeds on the wind? Or are we witnessing the most ordinary outcome of all, a universe filled with life that never needs to leave home? These are not questions for instruments, they are questions for centuries. In the end, the James Webb Space Telescope did more than detect molecules. It altered perspective. It reminded us that discovery is not an event, but a dialogue between data and imagination, between what we know and what we dare to ask. That faint spectral line across 120 light-years is not just science, it's communication. It's the universe whispering, "You are not alone." We may never meet the organisms of K218b. We may never decipher their biology or witness their oceans firsthand. But knowing they exist changes everything. It redefines what it means to be human, to live on a planet that is no longer singular, in a cosmos that has become once again alive. In every generation there is a moment when wonder outweighs fear, when curiosity eclipses doubt. The 99% world is that moment. The telescope that looked backward in time has shown us our own future, a civilization capable of listening to the universe and of hearing it answer.